Okay, so I want to introduce the whole workflow for thermal analysis using Climate Studio. But I wanted to give a little bit of an intro first. Remember, like the point of this class, really, the macro point is just to start developing digital workflows for simulation that hopefully students will carry forward and not just the specifics, but the concept that you can model. You can simulate performance of any type that you want, or lots of different types that you want as you're designing. And that really, if you don't do that from the beginning, you're going to undercut your designs because you won't be able to do what you think or what you were planning because it won't be practical. And so, why is that true? Um, uh, I think the main reason it's true is because buildings have changed incredibly in the last, let's say, 100 years or whatever number you want to put on it. Um, and and I'm always bringing up the Guggenheim because I love the Guggenheim. It's such an incredible building. Um, but it's a good example, I think, of this is that, so if we look at a section of the Guggenheim, that poche of that envelope is pretty accurate because, I mean, I have not studied the Guggenheim. Maybe there's some, it's always dangerous to say things if you haven't really studied in detail, but pretty sure it's just concrete. There's no insulation. There's a pretty simple initial mechanical system. There's no real consideration of interior comfort in the way we have come to expect it or need it in the contemporary world. Um, and then on the right, you have just a sort of state of the art basic house envelope now. This is from uh, a passive house manual. Passive house being a high performance building standard. But the point being very complicated now. The building envelope, the passive envelope of the building uh, has become very complicated in recent years, and it's because of several things. One is that we are demanding a lot more control of the interior environment, and that causes us to need to have more of a separation between the inside and the outside. And then once you do that, you need to understand building science and anticipate how um, liquid water, water vapor, heat, and relative humidity. Uh, the point to make about this is that its mechanical systems have changed drastically. This is a larger time frame here, 1200 the 13th century to today. But the point being that even in a lot of the precedents that you might have studied in class, there wasn't any mechanical system, or there literally like in a fancy um, castle, they would have a fire on the floor with no chimney, right? So very basic. And our mechanical systems now are really complicated and have um, taken over a lot of the volume of the building. So, for example, this is mechanical system graphic here. If we, I think I've got, yeah, I love this. Oops, I love this video. This is just the HVAC system for this typical tower building. There's no walls here. There's nothing other than HVAC, and it's already a building, right? It looks like a building. It's an architecture. So that dynamic is huge in architecture today. And if we ignore that as architects, then we're really going to be taken out of the equation. So, building have changed massively. In order to really understand this building on the right and to be able to design it from a schematic standpoint to a finished built project, um, we need to be thinking about a lot of variables, all of it from the very beginning that we weren't thinking about even 50 years ago. Um, Another point to make as we start to think about thermal modeling is the concept or the fact of volume to surface area ratio. This is a really simple idea, but it's huge in terms of modeling and in the architectural space and building design. So my background is in very small buildings, houses, basically. And so if you're trying to design a house that is conscious of its interaction with heat movement, um, you are thinking a lot about the building envelope, the volume that separates the inside from the outside, and that's because smaller buildings are what is called heat load dominated. I'm sorry, skin load dominated, and the reason for that is that they have a lot of surface area to volume. And so in the surface area of the exterior surface area of the building is where the heat moves in or out. And so if you have a lot of surface area to your interior in relationship to your interior space, then the envelope becomes hyper important. As we increase the size of our building enclosure, um, we reduce that ratio. So this is the shape on the left is my starting point. The one on the right, I scaled 3 times. Its volume is 27,000 now, where the other one was 1,000, and the surface area is only, but the surface area is 4,500 to 500. So the ratio in the first was 2 to 1 volume to surface area, and the second 6 to 1. So now we have much less of an effect of our building envelope on the performance of this building, on the amount of heat that's moving through the building. Um, so that's a huge thing. And so as you start designing larger buildings, you're going to have a different, or if you're already doing them, as you start thinking about this, you're going to have a different relationship between, or different concept of what the building envelope should be for a large building than a small building. Um, the other thing about large buildings, like if this were an office building, is that they're called typically in this space they're called internal load dominated. So this is skin load dominated. This is internal load dominated, and that's because um, in a building of this size, the equipment and the lighting and the people are generating enough heat to be a very significant portion of the heat load of the building. So here you're more concerned about what's going on inside the building, a little bit less concerned about the envelope itself. Here you're really focused on the envelope in this one as compared to this one. So that's a difference. Another thing that we just from the very beginning, you got to be thinking about, and I'm telling you, I've been doing this a long time, and it still drives me crazy, um, is our units. Um, I love this map because it just shows how, I mean, the United States is a great place, but we are so stubborn, and it's just to the point of absurdity. These are the 3 countries that use the inch-pound system still in the world, in the entire world. Um, uh, the United States, Liberia, and Myanmar, and then there's some use still in the United Kingdom, which is where the inch-pound system started, right? I mean, a foot I think was some king's foot length. I mean, I think I haven't. I think that's true. Anyway, it's if you've used both, you realize how elegant the metric system is, how organized, and how haphazard the IP system is. The problem is that in the United States, as far as I know, we're still using the IP system. You guys are, all, everyone who's got who are interns, I'm sure the project you're working on are inch pound. So you've got to be very, very conscious of units at all times because a lot of the modeling software and other things you're going to be looking at, specs and things, are going to be in metric, and so you need to get more. You need to get adept at converting between metric and IP. And so I really encourage everybody to start, if you're not doing it already, using Excel. Like this is, as I've been working on this modeling to prepare for this class, I've been, I just created this little modeler myself, or this little calculator to make conversions on the fly as I was needing them. And you need to start just thinking in both systems. And I'm just telling you from experience, this is something that's going to haunt you if you don't spend some time on it. All right. Um, so then we've talked about this before, that I want to create or I want to introduce Local Law 97 in this class. And the reason I don't want it to be a class about Local Law 97, there's some arcane things about it. We're not engineers. We can't really say that we're accurately modeling these buildings that we're playing with. This class I want to be a skills class, not a design class, because I think there's enough skills to learn here. Um, But I think it's important that we start understanding that the thermal modeling is not just about it's not well, for one thing, it's about money, right? You know, the less energy we use, the less money we're paying out. But of course, it costs more money initially, often if you're not designing carefully. So there's a trade-off with that, and we typically energy's cheap, and so we don't build very efficiently. But so that's just not going to work anymore. We now have a legal structure in the New York City, at least in New York City, that's going to require very energy efficient buildings. Um, I was talking to an architect the other day, an academic architect, and he was just going, they're going to change that. They'll make it. Don't even worry about it because that's going to get, they'll get rid of that law. I found that shocking because, I mean, first of all, this is a great law. We need to do this for climate change reasons. But also, it's the law. I mean, I mean, it's such a hide your head in the sand attitude. So let's not take that. Let's just start playing around with this or understand that it's here, that it's a reality. It's starting next year in 2024. Um, the basic idea is that any building larger than 25,000 square feet is going to have very stringent carbon emission requirements. Um, and I'll get more, I'll think of how exactly to introduce this in the class and be more efficient. I'm just, it's a Saturday morning. I'm just making these videos for you guys as an introduction. So I'm rambling a little bit. But the idea is that, so it's a pretty simple, straightforward idea. There's going to be, the code occupant designations are going to have specific carbon emission uh, thresholds tons of carbon per square foot. That's what you're seeing here. And here's just our tried and true, well-known use types, and they have specific metrics that we're gonna have to meet. And it's pretty simple. The one I've been using is office. But already you see here, like, what is this? We've got two different numbers because they started with this one, I think, and now they've transitioned to this one. I think this is a different law, maybe. So it's we're not going to be environmental lawyers here, but I want us to use this metric because it's real and it's just something that it gives us a game to play that we need to get toward some level of performance in the thermal model. It's also why I think the thermal model is a good thing to start with because we need to, in design, you need to start somewhere and have a focus and move out from there. The thermal model will allow us just to kind of see the dynamic of how this works with uh, envelope and mechanical system, et cetera, full building design, which this is what this class is, it's a co-requisite for the comprehensive studio. Um, and then once we kind of understand how possible it is to, or how difficult it is, or however we want to see it, with a simple model, get to this level, then we go out from there and say, well, what happens now if we start thinking about daylighting and other site-related aspects of the design? So that's my idea for now. It's kind of the opposite. People typically start with the site, but I think this makes sense, and we'll see what you guys think. Um, so I've showed you this before, but this is, there's just these real world resources. This is just a New York City map of where you can look at your project and see where you stand. If we done this with you before, I think, but if we go in here and just put in the Guggenheim Museum, because that's what we've been, I mentioned before, um, we see that according to this map, which is from the city, that in 2024, starting next year, unless the Guggenheim has done something to mitigate, it's going to have a $215,000 fine. I'm assuming they're going to have some kind of um, grandfather this project in, or there's a lot you can do with mechanical systems because this is a very large building, and so it's going to be internal heat load dominated. So they can do a lot with mechanical systems, and I think at least initially that's how they would deal with this issue. Um, but just saying that there's this very simple resource to use that people can experiment with, and then there's this great calculator that the same organization has created. Um, let's go to it. You can bring in, they have a sample building. So, and I have all these, of course, I will make all these links available so you guys can play with them if you want to. But I'm really just making a point here that this is a real world thing that we will use as a benchmark, and I'll provide the benchmarks. So I'm not sure how much we're actually going to play with this, but we may. I don't know. Anyway, so here's a sample building that they brought into this, and the point is that this building started out where it's not having a fine, but then it's gonna, because every 6 years heading towards 2050, the thresholds become more stringent. All the way down to 2015, the threshold is zero, so that's pretty crazy. So the fines go up and up and up on this project. If we put the Guggenheim in here, so you can also load buildings from that map. Oops, that's the wrong thing. Find your building. If I put in Guggenheim, then it loads it, and you can um, use this tool for existing projects. The way it basically works is that you have your square footage. You could define this, like I think that the sample building has different use, it's a mixed use building. And then it's defining how much the power usage, or I'm sorry, the energy usage from different sources, because of course, hot water is going to maybe be natural gas or fuel oil, or if it's a heat pump, it'll be electricity. Anyway, there's a whole metric, I mean, a whole uh, world of energy sources. The point is just a little spreadsheet I made to play around with this, is that these are from the code, that each electricity source has a different output of CO2 because they are cleaner or more dirty. Electricity actually has a pretty high one, the highest, because there's a lot of, uh, regardless of how you make the electricity at a central plant, you lose a lot through distribution. So through like if it's a steam plant, you think of it as a huge turbine turning around, a lot of friction. And then you have very long wires that you're sending this, electricity through. So you have a lot of, you're losing load through that process of shipping the electricity. So anyway, the point being that it's more complicated than just figuring out how much energy you're using. Another reason why we probably won't get into too much detail on it, but that's what this is doing. It's if you just have a power bill from your project, you can put it into this modeler, and it gives you this nice layout of where you stand, and you can use this to make simple strategies on how you would, like for example, one in a building that has a lot of electrical usage like this. Um, the initial thing, which is not good in the long run, would be to switch to natural gas. It's going to lower just by switching, if you could change your mechanical system to where you were using more natural gas than electricity, then you would be saving carbon. Um, okay, and so then for us though, these are outputs from Climate Studio, a thermal model. And so the point is here that we will learn how to do a thermal analysis in Climate Studio of whatever it is that we're modeling, and then then we have access to a lot of data that's very clear and easy to access and manipulate. So, for example, in this case, we have this is the same run. Um, we see we have site EUI, which is the energy use intensity, is the amount of energy that the building uses per unit of, uh, this is said that energy use intensity is the amount of energy that the building is using on site. Then we have its carbon footprint based on their own metrics, which we'll talk about at some point. Cost, because you can put in cost, et cetera, et cetera. Um, but beyond this macro set of data, we have the energy use broken down into in different ways. And the point is here that then we can use this data from our model to think about how we want to iterate. So for example, we see here that we have a really large cooling load and some heating load. Definitely. This is lighting, and the gray is power. So we can save some energy just by changing our lighting. Like maybe this is incandescent lights, and we can change them to LEDs and drop this without having to do anything infrastructural. Um, Our windows here, we see that we're getting some gain in the summer that we might want to, maybe we could change our glazing or do some shading here. There's some work on the envelope we could do and also on infiltration. So you can see that then by doing a model, it's not just like what's the value we get from it and then move on. It's a way of it's the main function of the model in my mind it's an iterative tool to help us design. And so the idea would be that if we get to a point where, and I think you'll see that it's pretty easy to do once you kind of know how to do it, that as you're developing your studio project, you could be always checking back on these metrics from the thermal analysis and other analyses you've done because they'll be set up and just think about, oh, I made that change. Do I really need to do that? Oh, that's going to take me way out of my some metric that I've determined, and let me reconsider or see how I can tweak it now so that I know that I can keep moving rather than later having to do some kind of triage. Um, okay, so that's the basic idea. This is a thermal model that I'm showing you. So let's go and look at Climate Studio and how we generate this data.